In this video, what I'm going to do is I'm going to talk about the so-called laws of logic, types of logic, as well as some things regarding statements and arguments. Now, the reason why we're doing stuff on logic before we get to stuff on ethics is because I think having a little bit of background in logic will give you some vocabulary and some theoretical equipment to be able to critique and analyze some things in ethics more effectively. So, let's start by taking a look at the so-called laws of logic.
All right, the first thing I want to talk about is the notion of the so-called laws of logic. Now, when it comes to the history of describing logic in the so-called Western tradition, the first person to really articulate various features of logic with a great kind of specificity was Aristotle, who lived in the 4th century BCE. And so Aristotle identified three fundamental principles of logic. What he means by laws of logic are, here's the three fundamental things you have to accept, period. And there's kind of an insinuation here that everybody accepts these. There's no way that you could do any kind of logical reasoning without accepting these principles, these laws. Therefore, everybody believes in them, and that even if you're going to try and refute logic and say, here's how I'm going to disprove logic, you couldn't really do so in any meaningful way without accepting these principles, is what Aristotle is getting at, and his successors. And this is echoed in some other logical traditions in other non-Greek societies as well. You kind of see elements that are like this in, say, the Nyaya Sutras by Akshapada Gautama in India and other places. But here, the Greek tradition is what's most well known in the so-called Western tradition, so that's why I'm going to stick here. And he says these things pretty succinctly and in a threefold way. So here are the three basic laws of logic. The first one is the law of identity. And this one is probably the most simple, and here's what Aristotle means when he says these things are obvious. The law of identity is simply that a thing is the same as itself. What does that mean? It really is as simple as it sounds. So here's a quote from Aristotle's Metaphysics that I have here. Now, to ask why a thing is the same as itself is no question, because when we ask the reason of a thing, the fact must first be evident that, for example, when we say something like the moon suffers an eclipse, and because it is itself is the one explanation and reason which applies to all questions such as why is a man man, or why is a cultured person cultured. What Aristotle's saying here is that when we have meaningful language, the law of identity is obvious. When I say the moon has an eclipse, what am I talking about? I'm talking about the moon and not something else. So that when we use language, when we refer to, especially nouns, but it could be verbs and adjectives as well. The green pen. What do you mean by green? I mean green, not some other thing, blue or red. When I say pen, I mean pen and not something else. Now, sometimes we can agree to talk in like a code, okay? And we'd be like, point this green pen here, and I say, the blue pen. And maybe blue we're using as a code word for green for some reason. Sometimes this happens. But basically, when we're talking about something, we're talking about that thing and not something else. Aristotle says this is an obvious feature of language, that when we're talking, when we're communicating, we mean what we say. And we're referring to the objects that we say that we're referring to and not some other thing. And he says this is super, super obvious. When I talk about something, I mean what I'm talking about. You have to accept that. You can't just someone say something and go, oh, you must be talking about this other thing. Well, they're talking about this, or I'm talking about this. So that's the law of identity. Something is itself and not something else. Water is water. The moon is the moon. I am me. All right, the next one is the law of non-contradiction. Now, this is basically a variation on the same theme. So if the law of identity is true, these other two laws of logic are sort of corollaries. That is to say, they should also be obvious if the law of identity is true. So the law of non-contradiction works this way. A thing cannot both be and not be at the same time and in the same sense. So I'm going to read a little bit of this from Aristotle here, not the whole quotation, but that way you can see the context of where it's coming from. Aristotle says, clearly then, it's a principle of this kind that is the most certain of all principles. Let us next state what this principle is. It is impossible for the same attribute at once to belong and not to belong to the same thing and in the same relation. So, something can't both be and not be at the same time and in the same sense. That's a contradiction. Now, sometimes we'll use the word contradiction to mean something being inconsistent. So let's say, Bob is a hardworking person, but he's having a lazy day. Well, Bob is both hardworking and lazy. That seems to be a contradiction. Or sometimes we do this with politics. Someone's a Republican, but on this view they're kind of liberal. That's a contradiction. Or someone's a Democrat, but on this point they're conservative. That's a contradiction. That might be inconsistent, but it's not necessarily a contradiction. A contradiction is saying something and then explicitly saying the opposite. Okay, it'd be like me saying, for example, at the time of me doing this, it happens to be Sunday. To say today is Sunday and not Sunday, that's a contradiction. All right, to say something and immediately the exact same thing with a not or a negation in front of it, that's what a contradiction is. But Aristotle qualifies it. He says, at the same time and in the same sense. So something can't both be and not be at the same time in the same sense. So I could say, for example, let's say I'm in a classroom, it's 8 o'clock in the morning, I'm super tired. There's a sense in which I can say, I'm here, but I'm not here. Is that a contradiction? Well, it might look like one at first glance. But what's going on there is probably I'm talking about here in the first sense, meaning my physical presence, and here in the second sense, meaning my mental presence. So I'm talking about two different senses. So that's not a contradiction, even though it may look like one. Or the notion of time. For example, right now I'm in my office. But at other times today, I won't be in my office. So today, on this Sunday, I was in my office and I was not in my office. That's a contradiction. No, it's not, because of the notion of time. Something can't both be and not be at the same time in the same sense. I can't both be in my office and not be in my office at the exact same time. That's the issue with the law of non-contradiction. And so with contradictions, a contradiction is an explicit saying of opposites. Okay, sometimes we think things that are different are opposites. That's not the case, as we'll see in the next law of logic. So the next law of logic is actually the law of excluded middle. This is that either a proposition or a statement is true. We'll talk about what propositions or statements are, basically something that we can say that's true or false, or they're not. So that's why he says here at the beginning of this quotation from the Metaphysics, nor indeed can there be any intermediate between contrary statements. But of one thing, we must either assert or deny one thing, whatever it may be. So for example, earlier I said today is Sunday. Now, if I take the law of identity, when I say Sunday, I mean Sunday and not something else. If I take the law of non-contradiction, it can't be the case that it's both Sunday and not Sunday. That would be a contradiction. Unless I mean something else, but maybe I'm looking at some other kind of calendar. Oh, it's technically not Sunday on the Gregorian versus some other calendar. The law of excluded middle says either it's Sunday or it's not. So that's not the same thing as saying it's Sunday or it's Monday. Monday is a different day. Monday is not the opposite of Sunday, because it could be, if I say Sunday or it's not, it could be Monday, it could be Tuesday, it could be Wednesday, it could be Thursday. There are 6 other options. So Monday is not the opposite of Sunday. Tuesday is not the opposite of Sunday. What's the opposite of Sunday? Not Sunday. And so the law of excluded middle says there's no middle ground between a statement. Either something's true or it's not. You've heard people say, what's going to happen when you go to the game this Sunday? Well, we'll win or we won't. Yep. Law of excluded middle. You might be thinking there, well, we tie. Well, if you tie, did you win? No. So there's a sense in which either you win or you don't, in terms of being the victor. Aristotle says there's not a middle ground. Now, some logicians, some scientists, some mathematicians object to this one the most. They say there's instances where this is not actually the case. I don't want to really get into that here. Simply, I want to say at this point, the law of excluded middle, the law of non-contradiction, the law of identity, Aristotle says, listen, to do any conversation you've ever had assumes these principles. I'm not just talking about doing work in math or work in logic. Anytime you've ever talked with anybody else about anything, you're assuming, so says Aristotle, all these principles, that when you're talking about something, you mean what you say, you don't believe that opposites are true, okay, explicit opposites. That's what I mean by contradictions there. All right, it's both, like we might say, I'm happy and sad. Is that a contradiction? No. I'm happy and I'm not happy in the exact same way. That would be a contradiction. Okay, like I said, inconsistency is fine, contradictions are not. And law of excluded middle, something's either true or it isn't. Okay, there's no middle ground. That's what the law of excluded middle is. So for the sake of your first quiz, it's not that I want you to know the nuances of all these for the last 2,500 years. Just be able to recognize them, which is to say, know that, when I say the law of identity, which one am I talking about? Am I talking about something is the same as itself? Am I talking about something cannot both be and not be at the same time in the same sense? Or am I talking about a proposition is true or its negation is true? So if you can at least identify the names with their technical definitions, you'll be good. But this is also basically to help you understand what's going on in logic. So that's the basic framework, according to Aristotle. Everything else rests on that. So where do we go from here? Now there's some particular things I want to get into in logic. Notions of arguments, statements, different kinds of logic. Let's get into that. So the next thing I want to do is talk about the notion of arguments and statements, at least in the context of talking about logic. So what do I mean by an argument? What do I mean by a statement? You've probably heard the words valid and invalid and sound. That's a strong argument. That's a weak argument. What do all those things mean? Well, in order to get to that, let's start by talking about the different kinds of logic. Here's the three most basic species of logic: deduction, induction, and abduction. All of these come from the Latin word ducere, which means to lead. Like a duke, where duke is like a leader. These each mean to lead in some different way. So deduction literally means to lead down. Induction, to lead into. Abduction, to lead away. You'll notice there is no seduction or seduction on the list, which means to lead astray. That's not logic. That's just cheating. So that's not on this list. Occasionally I'll get someone do a fill in the blank on these questions, but there is such a thing as seductive logic. No, there's deduction, induction, and abduction, aka deductive logic, inductive logic, and abductive logic. The problem is these are all different kinds of logic, and they have different criteria, and they do different things. So the main one that we're going to talk about in this course, like 99.9% of what we're going to do, is deductive logic. You've seen it before. It's the most basic form of math, or as the British say, maths, based on the axioms that we have in place. So deductive logic is where you have logical arguments, and I'll talk more about what arguments are here in a moment, which can be measured in terms of validity and soundness. Basically, if the premises are true, it's impossible for the conclusion to be false. If you got all your material together, you know what the answer is going to be. And so, for example, on standard axiomatic systems, if I say, what is 2 plus 2, or I put it in an algebraic way, I say 2 plus 2 equals x, solve for x, or, what does 2 plus 2 equal? What's the answer? Well, assuming we're using standard axioms, the answer is 4. Could it be 5? Well, in a certain sense, yes. I don't want to get into that here, right? It could be based on different axiomatic systems, depending on what we mean by 2. But I think on the standard way that you learned it in elementary school, when I say 2 plus 2, what does it equal? The answer is going to be 4. Now, you might do some equivalent of 4. You might say, oh, it's, 16 over 4 as a fraction. Well, that's the same thing as 4 if you want. You're just trying to get fancy about it. Basically, deduction works this way. If you have all the stuff together, there's no way that your conclusion could be wrong. 0% chance. If you know what 2 is, based on the system you're using, and you say 2 plus 2, you know it's going to be 4. Okay, another example, deductive logic, geometry. I was using arithmetic there, and algebra, geometry. If I say a triangle has 3 sides, and then I see a figure that has 3 sides in 2 dimensions. Could it be a square? Could it be a circle? No, it's a triangle. Okay, that doesn't mean you know whether it's isosceles or equilateral or right triangle. You don't even need to know those things. Just listen. If it's got 3 sides, it's a triangle. If it's got 8 sides, it's an octagon. If it's got 4 sides, it's a quadrilateral. Might be some other. You might be thinking, oh, it's a square. Maybe, maybe not. But we can at least do that. Like, I think the easiest one there is if it's got 3 sides, it's a triangle. There's no way we could be wrong. Okay, what if it has 3 sides and it's a square? There's no 3-sided squares. There's no round circles. There's no circular squares. So the way deduction basically works is if you've got all the data, there's no way you can be wrong. Like 0% chance. Okay, assuming you're doing everything right in the system that you're using. That's one kind of logic, and we're going to focus mainly on that one. Okay, if we've got the right stuff going in, we can get the right stuff going out. But that's not the only kind of logic that there is. There's some kinds of logic which it's possible to err, to make mistakes. There's a certain sense in which we can do that in deduction too, for different reasons, but not based on the premises that we have or the information that we've got going in. So inductive logic, or induction, which literally means to lead into, is a kind of logic where arguments are constructed based on a given sample, and then we generalize or universalize from those instances. So one example of this would be like polling data. When people interview people and say, who's going to vote for whom, and then we say, okay, 90% of the people we interviewed say they're going to vote for this person. We can say, oh, this is the likelihood or the probability of this going to be happening. Okay, so that's inductive logic, where we're making probabilistic generalizations based on samples that we have. A lot of science is done this way, like meteorological science is done this way, based on what we understand about pressure systems, based on hurricanes that we had in the past. We say this is the way that, based on the the various instances that we've had happen in the past. This is the way we predict this is going to happen, but it's a lot more flexible. Same thing with polling. We've polled, we think here's what's going to happen, and then I think people saw that happen in the 2016 election. Here's what we think is going to happen going in terms of the polling. That didn't happen that way because it's fallible. That is, it's possible to make mistakes even based on good data. And we say what makes an argument strong in inductive logic is that you have lots of data, you have lots of instances to support your position. An example of a weak argument in inductive logic or in statistics would be like, I interviewed one person, they said they're going to vote for this person, so I say 100% of people interviewed say they're going to vote for this person. Weak, because I didn't have a lot of instances to back on what I'm saying. Whereas a lot of, say, laws of physics have this kind of inductive backup. How do we know things like, how do we know if water is going to freeze at 32 degrees Fahrenheit? Well, because it's been measured multiple times that it will do that. Now, there might be counterexamples where it doesn't, based on, say, altitude or pressure or all kinds of other features. We haven't been every single instance in the universe where water freezes at 32 degrees Fahrenheit. We can say, based on, hey, there's a whole bunch of instances where that's confirmed. So we can say, listen, if it gets down to 32 degrees, it's probably going to freeze. That's the way induction works. High likelihood we're able to make declarations about things based on data analysis. But it's probabilistic. It's not definite. We don't know with the same kind of certainty. Like that whole triangle has three sides. I'm looking at something with three sides. It's a triangle, 100% certain. Apodectic certainty. Like you can't doubt it. Inductive logic, you can have high probability. Okay? 99% likelihood even. There's still a chance that you could be wrong. Okay, that's inductive logic. Abductive logic, on the other hand, is where we abduce, we lead out. So abduction is where arguments are made as likely hypotheses to explain existing conditions. Okay, so what we do is in abduction is we look at a situation and we think to ourselves, what made this happen? Now, like induction, it's possible for us to be wrong or mistaken much more easily than, say, in deduction. We might be right, but we might be wrong. So there's here, instead of probability with induction, we get necessity or certainty with deduction. We get probability with induction, and then we get likelihood of possibility with abduction. So what do I mean by that? Well, like criminal science is abductive, like detectives solving crimes. You know, you come into a crime scene, there's a murder victim on the ground, they've got a bullet hole in their chest. If you're a detective, were they stabbed? Maybe. But probably they were shot with a bullet, with a firearm. Okay, well, maybe the bullet materialized in their chest somehow. Maybe. Or it's more than likely that what happened was, and there's some inductive reasoning going on here too, that they were shot. So what you do in an abductive situation is you try and reason backwards from, okay, here's what I see, what made this happen? So criminal science is this way, like what made this happen? And we've seen it, that can be wrong. Have people been put on trial and convicted for crimes they didn't commit? Yes. Okay, and vice versa too, but that's not my point there. Medical science is also often abductive. So someone comes in with symptoms and you try and reason backwards. Oh, they've got these symptoms, they must have this. Oh, they didn't have that, came back negative, I guess we're going to have to do tests on something else. Medical science, we don't have an uproar over, oh, you said I was going to have this and I didn't. Maybe, based on the symptoms, we try and make abductions to figure out like what could be causing these symptoms. So that's also abduction as well. We do this often. If you came into your home, like you came in the front door and all your furniture and all like your television, everything was gone, I think it would be a wise abductive reason to think, oh, I've been robbed. Maybe there's other possibilities. Maybe someone was just like, no, I'm replacing all your stuff with better stuff. I'm just holding it for a while. But if you came home, like it's possible maybe you were moving and it was a surprise, or someone was getting you new furniture or whatever. All those things are possible. But abduction is where we try and say, when we come into a situation, we observe it. What made this happen? What are the conditions that made this possible? Okay, like in the case of coming home. Hey, all my stuff is gone. I guess new stuff's coming. Okay, from rooms to go or what have you. Probably not. You've probably been robbed. A lot of science is also abductive here. So abductive reasoning, like when geology looks at various layers of, or stratifications of rock layers in the earth and says, well, then the earth must have been like this in the Pleistocene or the Pliocene or the Miocene or the Eocene or the Oligocene and so on. Okay, they're able to look at those things and say, here's what was going on then. Okay, here's what caused the Cambrian explosion. Scientists do this all the time. Astrophysicists will say, based on the way the universe seems to be expanding now, we can extrapolate backwards using abduction and figure out if the universe is like this now and it's expanding, we can rewind the universe and see what it would have been like billions of years ago. Now, since that's abductive, it's possible that it's wrong. That doesn't mean don't trust it. It doesn't mean never abduce or induce. It's just that it's liable to be mistaken. We don't have the same kind of certainty as we do with deduction, like a triangle having three sides. There's no way we mess that one up. Induction depends on how much data we have to collect. And abduction, I think they're based too, or abductive reasoning is only so good as the observations that we have to back it up. A lot of that feedback comes from induction. But the problem with this is, if you ever read Sherlock Holmes, okay, the detective, or you're familiar with the character, Sherlock Holmes refers to all of this, especially abduction, with the word deduction. So these are the differences between them. Deduction is based on validity and soundness. If the premises are true, it's impossible for the conclusion to be false. Induction is where it's based on samples, and then those samples are universalized or generalized. We take a couple of instances. We say, okay, this happened a couple of times, so we can say probably this is going to happen. It could be wrong. In fact, it's a specific deductive fallacy when we do that. Then abduction is where we say, okay, here's what's going on. What caused this? So like right now, a good abductive argument would be like, okay, you're watching this video right now, so at some point Professor Burris in the past recorded a video in order to make this experience happen right now. That's a good abductive argument. It might be wrong. This could all be a deep fake, and this didn't happen. Maybe, but when we're using abduction there, we're trying to reason backward and figure out what made this possible. What could have made this happen? Those are the different kinds of logic that we're going to talk about here. The main one that we're going to talk about and examine from here is deduction. Okay. Now let's get into some more aspects of deductive logic. So I'm going to define some terms here. So first of all, let's talk about the notion of an argument. So colloquially, we use the term argument all the time to mean like we got into a fight with somebody. And sometimes people, even in the domain of logic, mean that as an argument, like we're fighting over two things, we're arguing. That's one thing. But an argument in logic, especially in deductive logic, is this. An argument is a series of statements, one of which the conclusion is affirmed on the basis of the others. And so the thing you're going for, like the verdict, is the conclusion. The stuff you use to back up the conclusion, those statements are called premises. So what's a statement? A proposition or a statement is a sentence that can be either true or false. So that can be something that we say, or something that we write down or type up. Something that we can utter in some way or can communicate in some way that can be either true or false. So something like Rex the dog is a Dalmatian. And maybe Rex is a dog, but Rex is a pit bull, in which case Rex the dog is a Dalmatian is false. But if Rex the dog is actually a Dalmatian, then that's true. So a statement is something that can be either true or false. There are some things that we can say that are neither true nor false. And so that's the following four things that I have here. Imperatives or commands are neither true nor false. So if I say something like, go to your room, true or false? Neither. It's neither true nor false. An imperative is not a statement. Now, so-and-so said, go to your room. That can be true or false. Just the saying itself, go to your room, is neither true nor false. That's the case with imperatives or commands. Also, inquiries or questions. Like, if I say, like, is today Monday? True or false? Well, the answer to the question, today is Monday, or it's not, it can be true or false. It is Monday or it's not. But any question is neither true nor false. They're devoid of any kind of truth content in that regard, or truth value. Proposals or suggestions. So if I said something like, let's get a puppy, true or false? Neither. Neither true nor false. Now the answer to that, let's get a puppy. Okay, I say, let's get a puppy. That can be true or false. But the proposal or the suggestion itself is neither true nor false. So imperatives, inquiries, proposals, neither true nor false, and therefore they are not statements in this regard because they have no truth value. And then the fourth kind is fairly obvious. That would be gibberish. So if I say, blah, 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 true or false? Nope. The notion of truth value does not apply. So statements are things that can be said that are either true or false. They have truth value. So moving on from there, now we can talk about arguments that are comprised of statements, conclusions, and premises. In deductive logic, an argument is valid if and only if, given that the premises are true, it's impossible for the conclusion to be false. Now, we've already kind of talked about this. So let me also say, too, the phrase if and only if, that'll come up again later in the semester. When we see if and only if, it's almost like an equal sign with words. So what that means is if an argument's valid, then given that the premises are true, it's impossible for the conclusion to be false. And if the premises are true and it's impossible for the conclusion to be false, then the argument is valid. That's what that means. So if the premises are true, there's no way the conclusion can be wrong. Like, hey, we've got an object here, it's got 3 sides, it's a triangle, there's no way that could be wrong. That would be a valid argument. An argument is invalid if and only if, given that the premises are true, it is possible. It might not be, but it's possible for the conclusion or the argument to be false. So that means any kind of induction or abduction is automatically invalid. Now, that doesn't mean we shouldn't listen to it, but it means it's invalid in a specifically deductive sense. All the invalid means here is that it's possible it could be wrong. Not that it is wrong, but that it could be. And so that's what it's meant by invalid here. So you'll hear people drop these words sometimes. Oh, that's a valid point. Colloquially, I'm fine with that. When someone says like a good point about something, like we should do this, that's a valid point. Fine, I wouldn't correct somebody in that. But in a strict deductive sense, something is only valid and only if it's impossible for the conclusion to be false when it comes to looking at logical arguments. And then in deduction, an argument is sound both if it's valid and its premises are in fact true. So there's times where we can have a valid argument where it actually doesn't work in reality. And if an argument's invalid, it's automatically unsound, period. So those are the 2 criteria that an argument has to be sound. It has to be both valid and it has to be, in fact, true. So let's take a look at a couple of examples to see what I mean by that. Here's a valid argument. This one I've brought up already. All triangles have 3 sides. The shape I'm looking at is a triangle. It has 3 sides, so the shape I'm looking at is a triangle. Valid argument. If the premises are true, if triangles really do have 3 sides, and the shape I'm observing really has 3 sides, then there's no way the conclusion here could be wrong. And the shape I'm looking at is a triangle. Period. 100%. No doubt. Valid argument. Invalid argument means maybe, but maybe not. Like it could be, but it doesn't follow with necessity. That means, when I say necessity, that means it has a mustness, or that it must be true. Maybe. Maybe not. So the example I have here, some people win the lottery. True, they do. I'm a person. Yeah, I am. So I'm going to win the lottery. Maybe, but also maybe not. No, it's possible. So it doesn't mean that when I do win the lottery, see, I told you I was right. That means because I'm a person, because I can win the lottery, I told you I was going to win the lottery. That doesn't prove anything. So the fact that it's possible it could be otherwise makes an argument invalid. So sometimes you can have a valid argument, though. It's still unsound because the premises are not, in fact, true. So consider this one. This next argument is valid because all that valid means is if the premises are true, then it's impossible for the conclusion to be false. It doesn't mean the premises are actually true. So it has this. All sharks are ninjas. All ninjas are wizards. Now, if all that's true, if sharks are ninjas and ninjas are wizards, then it follows all sharks are wizards. That's a valid argument. This is why when people say the word, like they throw around the word valid, it might not necessarily be helpful. This is a valid argument. If the premises are true, then the conclusion follows. But I think we could say it's unsound because the premises are not, in fact, true. Maybe some sharks are ninjas, but not all of them. And then sometimes, here's another kind of a mistake. We can have an invalid argument where everything that you said to start is true, but the way that you put it together doesn't work. So look, here's an argument where the things that were said at the beginning were true, and the conclusion sounds like it should be true, but it's not. And I think it's obvious here. But what happens is sometimes people make arguments like this last one with stuff that we're unfamiliar with, and therefore it will sound more reasonable. Like, oh, that makes sense. So here it sounds stupid. So if I say all dogs are animals, all cats are animals. Since they're both animals, all dogs are cats. No. I could say all dogs and cats are both animals. That would follow. But say here all dogs are cats. That's stupid. Just because dogs are animals and all cats are animals does not mean that all dogs are cats. It's like a Venn diagram where it's just one circle. So what's happening there is someone's doing something where everything they said is true. The first 2 points are true, and the third point, the conclusion sounds like it should kind of be true, but it doesn't actually follow from the premises. And then, like I said, when people are talking about things that are more technical, sometimes people use this kind of argument and will think it's true. Like if I said, all particular asynchronous axioms are accretions from some point in time t, but also in time t we have accretions that are from the substratum of point B, well then what that means is that all substratums are accretions from point A. I just made that up and I used a bunch of technical language and it sounds like it's good, but based on what I said, just in the form, it's stupid. Nothing makes sense from what I just said. And the point I just make is here in the example, it seems obvious, like that's wrong. But sometimes people will use technical, when people are saying things that are technical and we don't recognize the stuff, like with dogs and cats, it's obvious, but in other things, it might not be obvious. So someone might say something that we find confusing. We don't know if there's a mistake in there or not. Just be advised that that's a thing that happens.
All right, well, that wraps up talking about the different kinds of logic, the laws of logic. Next, I'll be doing one more video on logic where I go into so-called informal fallacies of logic. These are the don'ts of logic that come up quite a bit that I want you to be familiar with before we get into ethics. So that'll be the next video, and then after that, I'll be getting directly into some stuff on ethics.